Okay, now we're in section 3, naming and writing ionic formulas. So the rules for naming ionic compounds. Rule number 1, never use prefixes with ionic compounds. Prefixes meaning mono, di, tri, tetra, penta, hexa, septa or hepta, octo, nona, deca, and so on and so forth. You don't use those. Rule 2, common cations and anions, including polyatomic ions, are listed on table 6.8 on page 182. And there's some more throughout, but you can find them in section 2 and 3 of your book. And rule 3, if the cation has only one possible oxidation state or charge, simply name the cation and the anion. These exist for most elements in groups 1 through 8 of the periodic table, or groups 1, 2, 13, 14, 15, 16, 17, and 18, depending on how you're naming it, or 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. Anyway, so we'll follow these rules and name the compounds I have listed here. The first one there is just calcium chloride. You just name those species. The second one there actually involves two polyatomic ions, which I'll get to later, but essentially I've taken this from one of my labs, and so I shouldn't have gotten to polyatomic ions yet, but I just copied and pasted this from my lab. Either way, if you look at table 6.8 on page 182, you'll find these species there. And so NH4 is a common polyatomic ion, and it's called ammonium. So the name of this is going to start with ammonium. The second species there is another polyatomic ion, NO3, which is nitrate. So NH4NO3 is ammonium nitrate. The third ionic compound here is aluminum chloride. You can just name those species there. And the last one is going to be a barium ion with a chromate ion, and so this is barium chromate. Now, the chromate ion I don't think I can see it in your book on that table 6.8, but it is in one of the labs we'll go over later on. I wouldn't give that to you on a test though, so you don't need to worry about that, but you can Google it. The CrO4 is a chromate. And then an older, outdated nomenclature system that you may still encounter for when the cation is a transition metal. That's groups 3B through 2B, or 3 through 12 in the periodic table. Those are the transition metals, or simply the D block of the periodic table. So if you encounter those ions, such as iron, they have more than one possible oxidation state or charge. We have to use suffixes on those, such as OUS or IC, to signify lower and higher oxidation states, respectively. This system, however, can be unclear when more than two oxidation states are possible. Like manganese has 3 or even 4 different possible charges that it can have, so it's not usable to use just 2 different things. So chemists have come up with this Roman numeral system, and in the Roman numeral system you use Roman numerals to indicate the positive charge of the atom or the oxidation state. There's no space between the cation and the numeral in parentheses to identify metal oxidation states with transition metals. Therefore, a copper 1+ ion would be called copper 1, and a copper 2+ ion would be called copper 2. So if we're naming these compounds, I've already got the names there for you. FeCl3 is iron 3 chloride. We know that because chlorine is not a transition metal and it's always a -1. So if we have 3 times -1, that's going to be a -3 overall charge. Every species, every compound ever has a net 0 charge. So that means the iron must be a +3. So it's going to be Fe3 plus 3 Cl minuses, giving us FeCl3, and the name of it is iron 3 chloride. Now for the second compound there, we have iron again and NO2, and you can see here there are 2 nitrates because, sorry, not nitrates, nitrites. There are 2 nitrites because that second 2 comes after parentheses. This would indicate 2 oxygen atoms for each 1 nitrogen atom. Okay. In total, there's going to be 4 oxygen atoms in this ionic compound now. So we've got FeNO2, which is called iron 2 nitrate. If you look in table 6.8, you can find an NO2. It's an NO2 minus. Since we have 2 -1s, we have a net charge of -2 from the nitrites. That means the iron has to be a 2 plus, so we get iron 2 nitrite. All right, so names of some common ionic compounds. Right here, Ki is potassium iodide. MgBr2 is magnesium bromide. Al2O3 is just aluminum oxide. You can see here, if I go retroactive, I take the 3 plus from the aluminum and I take the 2 minus from the oxygen. You get Al2 and then O3. Here are the common charges for many of the elements, the ones that will be used in this text, I guess, in order to talk about ionic compounds. This table here is table 6.8 on page 182, and so you can see it has ions with hydrogen, nitrogen, chlorine, carbon, sulfur, and phosphorus, and then associated names. So HO minus is one of the most important ions there. That's the hydroxide ion. If I was to write it, it would be HO minus, because the negative charge is on an oxygen atom. The ions of nitrogen, you have, here's your ammonium. It's a +1. But when it bonds with oxygen and forms ions, you have NO3 1 minus, which is a nitrate, NO2 1 minus, which is a nitrite. And you can see chlorine has 4 different ionic species or polyatomic ions that form with oxygen. There's perchlorate, chlorate, chlorite, and hypochlorite. Where that comes from, this is really hyperchlorate, hyper meaning above chlorate. There's chlorate, there's chlorite, and then we have hypochlorite meaning below. I don't know why they eliminated the high part of hyper in hyperchlorate, but they do it for all of them. So it's just perchlorate. Then you got carbons, you've got sulfurs, you've got phosphorus ions. You can see they follow a trend. Carbonate for carbon, hydrogen carbonate for HCO3 1 minus, cyanide for CN minus. The C2H3O2 minus is an acetate. That comes from acetic acid, which is vinegar. Sulfur, it has SO4 2 minus is sulfate. HSO4 1 minus is hydrogen sulfate. SO3 2- is sulfite, and HSO3 1- is hydrogen sulfite. Phosphorus goes from phosphate to hydrogen phosphate to dihydrogen phosphate and then to phosphite. This table here shows some ionic compounds that contain polyatomic ions. So you can see there's aluminum phosphate, AlPO4. It has the medical uses for these. Aluminum sulfate, Al2SO4 is an antiperspirant and anti-infective. Barium sulfate is a contrast medium for X-rays because it does not, or because it absorbs X-rays, X-rays don't pass through it. So you can see, like if someone ingests barium sulfate, you can see where the digested products are going to. Calcium carbonate is used as an antacid or a calcium supplement. Calcium phosphate is a calcium dietary supplement as well. Calcium sulfate is used in plaster, or like, if you break your arm, the cast is made out of that. Magnesium sulfate is in Epsom salts. It's a not diuretic. It's a laxative in a sense. Cathartic. Potassium carbonate is an alkalizer. It's a diuretic. Silver nitrate is a topical anti-infective agent. It will turn your skin black though if you get it on you, but at least you know that you have killed all the bacteria and things on there. Baking soda is NaHCO3, sodium hydrogen carbonate, or sodium bicarbonate. You use it in baking because it's baking soda, but it's also an antacid. And zinc phosphate is dental cement. All right, so the terms that we have covered in this lecture are anion, which are negatively charged species, or negatively charged ions, cations, which are positively charged ions, chemical formulas, which tell you the number of each element in a compound, an ion, which is a charged species, whether it's positive or minus. The ionic charge of an ion is the magnitude of it and the sign of it. Is it a +3 or -3 or what? Ionic compounds are made up of electrostatically attracted, oppositely charged species. And then you have octet and octet rule, which just states that elements of, or I should say atoms of an element want to obtain 8 valence electrons in order to be stable. And then polyatomic ions are those that are ions that have more than one atom bonded together and is charged at the same time.